I don't know.
So you can use this one. You will have your presentation going here,
Right.
as well as there, so you can manage that. People do this, or you can point that there.
So moving the thing on is what?
I don't like the red. Usually it's not good. The green is better, but that's what they have here.
I've got my own.
Green.
Well, no, red.
Red is not good. That's Paul May discovered that is people that daltonic they don't see.
Okay. Well, I can hold this one a bit still,
Okay.
more still than that. So. Yeah.
That's it.
So this is moving up and down as usual.
You can also do this here.
Probably find it easier. Yeah.
If you go ahead, you can manage here.
All right. Can I try this? Because my finger.
No, go there, go there.
Is it touch screen?
Onde é que está o rato? Ah, está aqui, está aqui.
Dá licença. Muito obrigado. So you can.
I prefer. Right. So I don't.
Perfect.
Okay. Are you good? Thank you.
I will ask to be careful with the water, okay? Because one time we had not the water, but a glass of water. The speaker, and then the water was to the
And the
ground.
electrics. Oh, God, right. I'll have a sip now.
Have a nice lecture.
Thank you. I'll do my best.
Mas sabes porque é que ele não vai para casa mais cedo? Sabes porque é que ele não vai para casa mais cedo? No divórcio. Não tem que ficar nada. Você começa a ter essa mulher com olho no rolo. Eu
Boa tarde a todos, mais uma vez, bem-vindos à parte final do nosso evento, que vai constituir provavelmente o ponto alto do mesmo, a lição Victor Mello Lecture. I will change to English because our invited is Professor David Haig. First I will present my colleagues here, Luís Guilherme Mello,
Boa tarde a todos.
And Roberto Coutinho, the president of IBMS.
Mais uma vez, boa tarde, e dizendo que é uma grande honra para a BMS, né, essa nossa lecture em conjunto com a Sociedade Portuguesa de Geotecnia.
Thank you. So on behalf of the Portuguese Geotechnical Society, it's also a pleasure for me to announce Professor David Haig. I have here a very extensive CV. If you allow me, I will resume a little bit. Okay, I'm sorry. So our invited today for the Victor Mello lecture is Professor David Haig. David Haig is a geotechnical engineer with more than 50 years of experience in research and practice in UK and around the world. He is a fellow of the Royal Society of the Royal Academy of Engineering. David specializes in forensic geotechnical engineering, drawing on his background in and knowledge of site characterization and the behavior of soils and rocks. He has been called on to investigate the stability and performance of reclamations, tailing dams, excavated and natural slopes, tunnels, road pavements, retaining structures and foundations to onshore and offshore structures. He has working on as consultant engineer. He is the founding director of one of the founding directors of GCG. Okay, and has been responsible for specialist advice to consulting firms, contractors, public authorities, solicitors, insurers, and oil and power companies on a large number of UK and overseas projects. He has been instrumental in establishing GCG since its formation in 1983. As one of the leading geotechnical consultancy companies focusing in technical excellence. The major works are technical audits. I can point out the Gulf Sea Gravity Platform, the Ship Lap COP Airport in Hong Kong, the Rio and Trio fixed link in Greece. Legal assignments also, has served as expert witness in litigation in the UK, Hong Kong, Singapore, USA, Australia, and Middle East. He served as an expert witness in the Committee of Inquiry into the Nickel Highway collapse in Singapore. Also, forensic investigations. External advisor, I can point out he was external advisor of geotechnical aspects of design and construction of Terminal 5 at Heathrow Airport, and also investigation and interpretation of ground conditions at the Port of Miami Tunnel. A lot of publications, presentations, and research. He is the lead author of the Syria Guide Engineering in the Lambert Group, and has published a number of state-of-art reports of the properties of the London clay. Dr. David Haig delivered also the 38th ranking lecture in 1998, and more recently he was invited to give the Biennial Sir Charles Ladd Memorial Lecture by the Boston Society of Civil Engineers in 2019. Finally, I will point out education. He was visiting professor at the Imperial College of London since 1993 to 2012. Also visiting professor at Singapore in 1999. Visiting research fellow in Nottingham University in 1988 and 1989. And also visiting a research fellow at Imperial College of London. He has several professional qualifications and memberships. And to finish, I will point out the scholarships awards. 2015 British Geotechnical Association Medal for Best Reviewed Paper. 2008 Geotechnical Research Medal, UK Institution of Civil Engineers. 2006 Spirit of Telford Award for contributions to engineering knowledge by the ICE. 2003 Telford Gold Medal, UK Institution of Civil Engineers. And 1993 British Geotechnical Society Prize for work on sampling and testing of soft clay. So, ladies and gentlemen, it is my pleasure to ask Professor David Haig to deliver his lecture about reflections and speculations. Thank you very much.
Thank you for the introduction. I don't know whether I say good evening or good afternoon, but let's go for good afternoon. First, I'd like to thank the Portuguese-Brazilian Society for inviting me to give the 9th de Mello lecture. I'm sorry the title has changed from the advertised version. As I got into trying to prepare something, I realized that I'd actually be talking about reflections and speculations. I met Victor de Mello in March 1977 when he came to Imperial College to give his ranking lecture. Thank you. So the lecture that he gave, the ranking lecture, demonstrated his depth of practical and theoretical knowledge, his enthusiasm, and his stamina. My recollection is that the lecture lasted 2 hours and 20 minutes. Apparently that was nothing compared to the dry run the day before, which lasted for 4 hours. Unlike most of his predecessors, my predecessors who've given the de Mello lecture, I've not had the privilege of working with Victor. Although we exchanged correspondence about my work at the Bothkenna soft clay site in the early 90s. I have, however, had the great pleasure of working with his son, Luis Guilherme de Mello, who is more than just a chip off the old block, if you know that expression. I've learned much from Lewis about his father, and of course I've had the advantage of this amazing book that Lewis and his sister put together. And it was the cover of the book with a picture on the right-hand side that made me think of Reflections. I just see Victor sitting there very pensive. You wonder just what he's planning, thinking about in that picture. And not looking at his reflection, of course. So I was inspired by the cover of Victor's book and also by the title of his ranking lecture to use the word reflections. Then I noticed that John Burland in his first de Mello lecture also used the word reflections. I'll come on to speculations shortly. I felt I had to put in this slide taken from another giant of geotechnics, Jim Mitchell, which sums up what I understand was the main features of Victor. And I'll leave you to read them. Another of the giants of geotechnics, Mikhail Yamakowski, began his de Mello lecture taking a quotation from Victor, who said, "We professionals beg less rapid novelties, more renewed viewing of what is already there." And that's where I want to start from. So I take this as my theme, reflecting on what developments there have been in some of the topics I touched on in my ranking lecture 26 years ago. There are two milestones in Victor's life that I've sort of also had. We both spent time at MIT. Victor was there in 1966, I believe, as a visiting professor, having effectively set up the department at MIT in his first day there. I went to MIT in 1983. He gave his ranking lecture in 1977, I gave mine in 1998. When I gave the ranking lecture, I hopped from topic to topic, looking at behavior and parameters in the context of flow slides in micaceous sands. As one of the attendees put it, changing the topic just as his eyelids were drooping or his seat was getting uncomfortable, I changed the topic. And he said that was enough to keep him awake. Hopefully we'll do the same today because I'm going to cover a number of different topics. So in a setting of flow failures and tailings, I'll reflect on localization, critical state, anisotropy of undrained strength and of instability in sedimented sands. I'll talk about void ratio and its spatial distribution, and sometime on moist tamped samples and understanding their behavior in terms of a chain reaction, which I believe also applies in the field. Lewis and Tiago Diaz at my office, GCG, helped me find a quote from Victor related to tailings dams. And he said this in 1980, which is worth bearing in mind that date compared to what's happened since in the world of tailings. He said, "To sum up, I allow myself to say that in the case of water dams, our experience has been so positive that the future invites the indispensable optimization of economics. On the other hand, when it comes to tailings dams, very justified are the concerns that, with time, the raises and the multiplication of diverse cases, the invitation to unpleasantness and failures is open and with a free ticket. We are only at the start, which favors us. Let us do the reconsiderations and revisions that the subject and the gravity of concern demand. I think this is pretty prophetic that he made that statement in 1980. When I went back to my ranking lecture, I realized how much speculation there was in it. In fact, I had some of the slides that were titled speculative. You'll recognize slides I've taken from the ranking lecture because mine was the last lecture to be given using plastic slides, so they have the obligatory blue background. So this is just one of the slides I used, and I suggested that shape and distribution of interaggregate pores determines anisotropy of undrained strength in soft clays and loose sands with fines. I said particle orientation determines anisotropy in stiff clays and shales. Contact orientation determines anisotropy in dense sands. And fissures with preferred orientation initiate on unloading along boundaries between distorted aggregates. Just to show the interest I had in those days with fabric, this was an SEM of the Bothkanna clay, the soft clay we tested at Imperial and various other universities. And I was always interested in these very large interaggregate pores that you can see both in the photograph and in the sketch. And it was this interest in macro voids and the void distribution that led me to suggest that it was this actual presence of the macrovoids in the shape that determined the anisotropy of the Bothkanna mottled clay. For the benefit of a couple of ladies in the audience who won't have a clue what I'm talking about, I have these two diagrams. On the left-hand side, I have some densely packed spheres, and shearing of that dense packing of spheres requires particles to rise up and climb over their neighbors, and this is dilatancy. Shearing of a loose packing on the right causes particles to nestle closer together to each other. This is contractancy. The nestling together in Welsh is cwtch, I believe. Thank you for the confirmation. Just another point that may be helpful to you is that shearing of loose and dense packings under the same confining stress ultimately brings the spheres to the same packing or density or void ratio. The voids between the particles can be filled with water or air or a mixture of both. If filled with water that cannot escape when sheared, the pressure in the water increases if the packing is loose and tries to contract. And that pressure reduces if the packing is dense and tries to dilate. So that's simplicity for soil mechanics, but the problem is particles are not spherical. They vary in shape and size. Their packing is not uniform at the same global void ratio. So the figure on the top right is one taken from a pretty old publication by a gentleman called Magami, who's just showing that you can get two entirely different packings of the same number of particles, and you can introduce these macro voids. So the packing is not uniform. Also, the soils have a fabric, an arrangement of particles that results in their properties being anisotropic, that is, varying with direction. The fabric and so anisotropy changes involves so that fabric and so anisotropy changes or evolves during shearing. So we're not talking about a constant situation. As we shear, we change the properties. So the same definitions that I used in the ranking lecture, I'll use now. The major principal stress, sigma 1, is at an angle alpha to the vertical, and the relative size of the intermediate principal stress, sigma 2, is given by the parameter small b. And so in a triaxial compression test, which we'll talk about, alpha, the major principal stress direction, is 0, it's vertical, and B is 0. Triaxial extension, alpha is 90 degrees and B is 1. I want to start by talking a little bit about discrete element modeling and microcomputed tomography, because I want to use some of the findings from that work in the speculations that I'm going to make. So discrete element modeling, on the right is a figure I've taken from one of Catherine O'Sullivan's publications, which shows the growth in the subject in terms of the number of publications. So the subject was in its infancy in 1998 when I did the Rankin lecture, and has grown exponentially. It predicts the displacements and rotations of discrete elements which represent idealized rigid soil particles. It provides information on forces at particle contacts, and so the development of strong force chains or load columns. It enables explanations of macroscale observations in terms of particulate microscale behavior. It provides reassurance on the validity of observations made in laboratory tests on soils, such as phase transformation, the effects of B and of alpha, as observed in the hollow cylinder apparatus. And it gives confidence in our understanding of instability in critical states. It supports intuition, and it corrects speculation. So it permits exploration of behavior under conditions that are not achievable in the laboratory, particularly at critical state. It enables the testing of identical samples without having to use mixed, rigid, and flexible boundaries, and without Platten restraints. But modeling particle shape is a challenge. Because of the developments in discrete element modeling and in microcomputed tomography, it shouldn't be necessary anymore to speculate about what happens at a particulate level. So I'm taking this as the last chance to speculate before everything gets proved to be wrong by these two techniques. So just one or two other findings which proved to be useful. Force chains are predicted from DEM. They're simply confirming what was known from photoelastic studies. So force chains are networks of contacting particles that are relatively highly stressed and aligned in the direction of the major principal stress. As the material is loaded, these force chains collapse or buckle and the new force chains are formed. A compact particle system, due to its highly redundant structure, quickly adapts to new loading directions by selecting new spatial distributions of favorably oriented contacts for transition of the forces in the strong sub-network. That's in a compact system. That's not the case in a loose particle system. Work done by Barreto showed that these force chains vary as you vary the parameter B, the value of the intermediate principal stress. So the value of B influences the force chains that develop because of its changing effect on the lateral support to the force chains. This is valuable when trying to understand what happens at critical state. The quasi-steady state. In the late 70s at Imperial College, a research student, Dr. Mustafa El-Gamrawi, was sent back to repeat his tests 2 or 3 times by the learned professor there, who didn't believe what he was observing in terms of what we now refer to as the quasi-steady state or the phase transformation. A 2D DM study by Yang and Dai shows that the quasi-steady state is a real behavior rather than a test-induced phenomenon. It's a transitional state in which spatial rearrangement of discrete particles sheared under constant volume conditions leads to the average number of contacts per particle decreasing to a minimum value before increasing gradually, and after that to an approximately constant value at large deformations associated with a steady state. At the steady state, deformation continues at constant volume, constant mean effective stress, constant shear stress, and constant velocity. So his work really reinforced what we thought we knew from our experiments. So microcomputed tomography, picture on the right taken from Salvatore shows the setup. A small sample, well, let me read what it says. So X-ray tomography allows the evolution of the three-dimensional 3D microstructure fabric of a small sample of sand to be followed while it deforms. Individual grains can be distinguished in time-lapse 3D images, and the full 3D kinematics of all the grains, and sliding, rolling, can be measured. I'm going to refer to the insights that it has provided on strain localization and particle movements during shear. This is a particularly interesting piece of work carried out on green lentils. So the lab experiments tested in triaxial compression with end restraint the behavior of these green lentils. The DEM study tried to simulate the experiments that were carried out. And I'm comparing here on the left the experimental data on the upper three photos with the DEM predictions on the lower three. And we're looking there at the incremental deviatoric strains. And you can see that the experiments are pretty well matched by the DEM studies. And what we're seeing here, of course, is localization, the concentration of strain in these portions of the darker, the red. On the right, similar conformation, this time looking at incremental volumetric strains. So the DEM, if you get the particle shape right, and if you get a few other parameters correct, can actually simulate what goes on in the laboratory sample. So let's talk a little bit about localization. A few examples of strain localization in triaxial tests. Strain localization involves bands of 10 to 15 grains particles wide, which dominate the material's macroscopic response and lead to global failure. So on the far left, you've got a sample in triaxial compression, which is bulging, but within which there is much localization. On the right-hand side, you have a sample which is shearing in triaxial extension. I want to just give you three statements from Professor Desroux, who is a leading figure in microcomputed tomography. And he made a number of statements in papers in 1996 and 2018, which I think are pretty profound statements. Strain localization is unavoidable and is ineluctable and omnipresent when sand is sheared. Carlos Santamarina says the same thing about it being omnipresent. Desroux went on to say in 2018, all other tests analyzed so far show the same pre-peak structurization of the deformation process, and this in a variety of different experimental conditions, whether initially dense or loose specimens, with slenderness ratios of 1 or 2, and with and without end lubrication. So effectively, you can't avoid localization when you're dealing with sands. He also pointed out that localization structure inside the specimens were clearly revealed by the density maps in the dense case. Conversely, in the loose specimens, it was difficult to observe localization structures because the density in the localized strain zones did not change significantly. So it's not to say that they're not there. In fact, they are there. It's just more difficult to observe them. So what does localization mean? Well, in dilatant soils, so soils that are sheared from a dense state, Dilatancy concentrates in a shear band, causing weakening in drained and slow undrained tests when pore water is drawn into the shear band. In fast undrained tests, pore water migration cannot occur and undrained strengths are higher. And this was pointed out by Sandro Sandroni in 1975. In drain tests involving dilation, decreasing stability is accompanied by reducing coordination number. The contacts are diminishing. But it's important to accept that localization occurs in contractant soils. So localization does develop in loose contractant soils, but it's difficult to observe, and it's self-healing in drained and slow undrained shearing, when locally higher pore pressures can dissipate out of the shear band. Under rapid undrained loading, the shear band cannot drain. Straining is concentrated in the band and the strength is reduced. This is why it's recommended to identify critical state in slow drain tests on loose samples, where the effects of localization can be minimized. On the top right, the two figures compare the DEM predictions of localization. The one marked as A is a test carried out with end restraint without lubricated ends. Test on the right is idealized testing of the same material. Again, these lentil-shaped grains, showing that there is some localization, but it's much less when you don't have the end effects in your triaxial test and when you're not using mixed boundaries. The bottom diagram is pretty typical of what happens in triaxial compression. Shear banding of standard-sized triaxial samples can be distributed, though, to such an extent that the sum of all the mechanisms does not show up in observations of the outside of the specimen. More or less cylindrical or barrel-like shape of the axisymmetric specimen strained in the laboratory tests may conceal internal complex structures involving strain localization. That's effectively another quote from Professor Desrues. So what are the triggers for strain localization? Is there any stage that we can look at where we're not impacted by it? Non-uniform dilation or non-uniform pore pressure generation and equilibration can be a trigger. Stress non-uniformities associated with boundary conditions, end restraint, mixed boundaries, pattern rotation, eccentricity in vertical alignment, stress concentrators such as fissures, other flaws. And I've highlighted the next one, heterogeneity. So initial and evolving variations in void ratio. If you're testing a sample which doesn't have uniform void ratio, you almost certainly will have localization. What I want to go on and show later is that you always have these non-uniformities in void ratio. Failure of a local strengthening agent, such as cementing, suction due to menisci, negative pore pressures accompanying, leading to cavitation, they can all be triggers. Orientation of plated particles can lead to localization. Loading direction, as we'll see, is important. And grain rotations seem to be a trigger for strain localization. Just wanted to mention this statement from a piece of work by Wang and Gutierrez. They said that global failure along the primary shear band prevails when the specimen length scale and length to height aspect ratio are small, while progressive failure becomes more likely when the specimen length scale and aspect ratio become larger. So localization introduces a scale effect. They went on to say that discretion should be exercised to select an appropriate shear device that best simulates the boundary conditions in the field. Very often, progressive failure is exactly the in situ failure mode governing the performance of geotechnical systems. This is interesting because we spend our lives trying to avoid localization by using end lubrication, by doing all these clever things. They're now suggesting that don't bother, just run tests where you get localization and try and interpret the data from those. I'm not sure. So, changing topics now to critical state. I want to look at is the critical state line nonlinear in E log P dash space? Does it depend on this parameter B? Does it depend on alpha? Is it actually attainable when you take into account particle shape and packing? On the left is the data published by Verdugo showing phase transformation lines and the ultimate steady state. So he found that it wasn't a straight line in E log P dash, it was curved, the curvature developing as the void ratio increases, as the material becomes looser. But I want to point out that he ran these tests on moist tamped samples. And I'm suggesting that at those high void ratios, there is important void ratio spatial distribution. This finding was confirmed by DEM work shown on the right-hand side by the group in Western Australia. So that's encouraging that the surface is curved. So I will adopt a curved surface later on. Does it depend on B? Well, we talked about force chains. Force chains exist at critical state. They've been observed again in DEM studies. So it's reasonable to assume that the critical state depends on B. At critical state, force chains continuously form and collapse and reform. So at critical state, there's simultaneous dilation and contraction. Does it differ between triaxial compression and extension? Two very careful experimentalists have presented data which throws some light on this. On the left is the data from Professor Vade and his colleagues who show two different lines, one for triaxial compression, one for triaxial extension. On the right, some data from Chujian and his colleagues showing that the critical state line is different for plane strain and triaxial, which is consistent with the idea that there is an impact of B which constrains particle movement. So, however, some more work on microcomputed tomography suggests that actually there is no difference. If you can look inside the shear zones, the shear bands that are occurring, then the critical state lines come together as opposed to so the dark points are two separate critical state lines, one for compression, one for extension. The upper solid line is formed when looking inside these shear zones and measuring the void ratio. I'm still not convinced by this, but I'm not sure you know exactly what's going on in those shear zones in terms of the B value. Does critical state depend on alpha? These are some pictures of particle orientation at a very high shear strain of 400% from Carrasco et al. And it's very clear that at critical state an anisotropic fabric develops. Elongated or platy particles align relative to loading direction, as do load columns, even in shear zones. If the loading direction is changed, for example, if you decide to rotate the principal stresses at critical state, the particles must reorientate, and the soil must undergo volumetric deformations to reach a new critical state. But is this feasible? Pre-existing particle arrangement can dominate subsequent behavior. And we'll look at that when we look at the effects of bedding in a subsequent slide. So continuing this question, is it attainable? if you consider localization, the early work by Professor Desrues in 1996 said that critical state is particularly well verified inside the observed localized band of deformation rather than the average of a complex strain field. So using his microcomputed tomography, he was able to look inside the shear bands, and he found that the curves came together for these loose and dense samples. The work was only done in triaxial compression. Is it attainable? Consider layering. I've taken these two photographs from Antonio's LAD lecture just to show you the tailings that were involved in the Brumadinho failure, how they vary, how there appears to be some layering there. And unless we can test large samples, which of course the other Antonio has done, we have a problem, because if we look on the left-hand side, that's a sketch of what the original sample may have looked like. If you remold that, and depending how you remold it, how you reform it, you could end up with an anisotropic fabric, or you could end up with an isotropic fabric. And neither of those are going to give you the behavior of the real material. And yet we test a lot of our materials by reconstituting them. So let's look a bit more closely at layering and what happens. And I'm looking at work here published in 2005 by Professor Yoshimi and his colleague. So they produced very carefully these segregated, stratified specimens shown on the left-hand side. They also produced, using exactly the same grading material, these homogeneous and uniform specimens shown on the right side of those two sketches. They then ran triaxial compression tests, and they found quite different steady state lines and quite different phase transformation lines. So layering is important, and you're not going to eliminate it very easily by shearing to large strains. And what about bedding? Okay, I've taken examples from two clays that we've been involved in testing. On the left-hand side is some data from the Louisville clay. This is data published by Serge Leroy and Pierre Leblond. And on the right, data from the Oxford clay, which show that as you rotate the principal stress direction, the bedding takes over. The bedding controls how failure will take place. When I was looking at this figure, I was interested by the fact that although I'm on the authorship list, we've used beta for the angle of the major principal stress to the vertical. I've worked with Professor Leroy for 40 years, and I still haven't been able to persuade him to move from beta to alpha. Similarly, he hasn't moved me from alpha to beta. But anyway, that's what we're talking about. Critical state, is it rate dependent? I think there are two sources of rate dependence at high rates of shear, particularly those associated with load control or maintained load. There's the time for pore water migration into or out of the shear band that we've talked about earlier, and in contractant soil, when there's no time for pore water migration out of the shear band, the undrained strength is reduced. There's also the possibility of collision of particles, and which will lead to a reduction in particle context. This is illustrated on the right-hand side. If you don't take anything else from this lecture, if you take this figure away, this is from my friend Chu Jan at NTU. We published this in 2009. So the diagram on the left is just a stress strain curve. The solid line from a deformation-controlled test, the broken line from a load-controlled test. The central figure is the effective stress paths from those two tests. And the third figure on the right is the time to failure. So obviously the solid line, which is the deformation controlled test, reaches failure over however long you want, 150 minutes in this case. Failure in the low control test is instantaneous. Why don't we do more low controlled testing? Because that's what's relevant so much more in the field. I looked at what people said about this, and I kept coming to the statement that deformation controlled loading has been recommended in the past to allow post-peak behavior to be observed. Yeah, well, that's the post-peak behavior under strain controlled loading, not the behavior that we should be interested in many cases. And the strength in these low control tests is pretty poorly defined, yet that's the one we're interested in certain methods of analysis. And going back to the work of Professor Wade, he said that only an inertial system can capture the true strain softening response of sand. Okay, back to the ranking lecture now, just for a couple of minutes on anisotropy of water and air pluviated loose sands in undrained shear. This was data we published in, it was in Satoru Shibuya's thesis in 1985, where we tested water pluviated Ham River sand in the hollow cylinder apparatus, shearing it with different directions of the major principal stress to the vertical. And the numbers on the right are the values of alpha in degrees. These tests were run with the parameter B equals 0. So you can see a major influence of the principal stress direction when you're shearing these sands. And the other thing we suggested at that time was to stack those different effective stress paths together in a three-dimensional space so that you can actually identify what we then called the collapsed surface and the dilatant region. It was very interesting because that slide was actually presented in the ranking lecture in 1998. 1998 was a bumper year for data on hollow cylinder tests. I've just taken two of them. This is data for Toyora sand, published by Yoshimi, as I said, in 1998. He did this test with a B equals 0.5 and found exactly the same pattern of behavior that we'd found in the Ham River sand. And if you look at the stress strain curves on the left, and you look at the tests at alpha of 15 degrees against the one of alpha at 75 degrees, it doesn't seem likely that they're heading for the same critical state. But of course, they're not going to get to the critical state because of localization that is inevitable in the hollow cylinder tests. Another set of data, this time from one of Wade's students, showing again the same pattern on a different sand at different relative densities. So another one of my speculation slides, that geomaterials show anisotropy of stiffness, strength, collapse potential and permeability because of anisotropic fabric, structure and stress state. Anisotropy evolves as fabric changes and is different therefore at small and large strains. Anisotropy is induced when fabric changes are permanent. Anisotropy of strength arises from directional dependence of volume change characteristics and/or of the failure envelope. A piece of DEM work that was of interest to me was looking inside a hollow cylinder sample when it was tested and looking at how the porosity changed in that sample as it was sheared with the principal stress at, in this case, I think 60 degrees to the bedding. You can see that concentrations of porosity develop, but they're really not particularly well developed until we are at failure, at peak. So it's encouraging that at least we can use the hollow cylinder data to look at this pre-peak behavior, or up to the point of instability. which brings me on to instability and collapse surfaces. As I said, the Rankin lecture was set in the context of flow slides in micaceous sands in Bangladesh. And we had to try to work out a slope angle for these cut slopes that were being dredged that would stand. And we ran simple shear tests on samples that had been moist tamped, and we ran undrained tests. That's the lower pale blue line. We then applied some shear drained to different levels and then turned off the drainage. And we found that there was a stress level that we could apply, in this case up to a shear stress of 36 kPa. At that point, so as soon as we turned the drainage off, the sample collapsed. So and that point would correspond to having a slope angle of, I can't remember now, 15, 20 degrees, something like that. So that's the data on the left that we just looked at. And we put that data together and suggested the existence of an instability line that divided unstable and stable behavior. What we didn't know at this time, of course, that this was a subject that had already been deeply studied by Professor Larde, by a gentleman called Sladen, and others. And that's the danger of not being involved in research yourself. You tend to stray into the experts' fields, and I should have apologized to those people at the beginning. So once we'd got that curve, we could suggest a slope angle for the infinite slope that could then be dredged, and that was done. As I said, instability has been looked at by many people. This is work done by, again, Chu Jan. These are triaxial compression tests. On the left is the effective stress paths for samples tested at different global void ratios. And the peak point of those effective stress paths, we have a line passing through those, and in this case passing through the origin, and that was defined as the instability line. The instability zone, of course, should end up at the critical state and is a zone between the instability line and the critical state line. And Chu Jan showed that the slope of the instability line depends on void ratio, global void ratio. So if you go back to our hollow cylinder tests, and now look at the effect of principal stress angle, principal stress rotation, and just put these instability lines on those curves, and I've done it for the Tiora sand and the Fraser River sand. So it's the same figures you've seen, but now with instability lines added. Then you can see on the left-hand side, if the slope of that instability line reduces as the alpha value increases, in the same way that the instability line is affected by void ratio. So you've got two factors to consider: the change in void ratio and the change in principal stress direction. Two other things we did at that time, trying to look at what might happen in those slopes. We ran drained and undrained tests on samples that have been anisotropically consolidated. The pink line shows the drain test that collapsed somewhere near this collapsed surface that we identified. So putting that data together, we could sort of define when collapse was likely to occur. Obviously, in these loose sands, it would occur under undrained loading, which is the pale blue. It could also occur under drained loading if that drained loading is not carried out under strict strain control, then it will collapse. If it's under strict strain control, you can actually pass through the collapsed surface and develop high strains. And going back to our earlier hollow cylinder data, we'd shown that simply rotating the principal stress directions could bring about collapse. So instability occurs before there is full mobilization of shearing resistance. The instability line inclination varies with void ratio, shearing mode, and direction. The instability line is least affected by localization because it occurs at small strains before particle rotation sets in. Instability can be triggered under undrained, drained, and partially drained conditions. However, under undrained conditions, only very loose sand can become unstable. Drained instability occurs when there is a reduction in effective mean stress for both loose and dense sand. Instability can be triggered by undrained rotation of principal stress directions at constant shear stress. Now, a little bit about void ratio. We rely heavily on measurements of global void ratio and pressure. So I'm just showing the classic data from Verdugo, which on the left-hand side shows the dependence of behavior in undrained triaxial compression on void ratio. And on the right, the importance of stress level at constant void ratio. But again, in the Rankine lecture, I've been fascinated by the work that Professor Frost was doing, looking at void ratio variations. He had to work with medium dense samples because he was using impregnation to look at void ratio variations. And he showed that there were fairly large variations in the void ratio in these samples. And he showed that that variation was much higher in moist tamp samples than in air pluviated samples. At the time, I wondered if this fact was related to the behavior, the different behavior we saw in moist tamps and air pluviated and water pluviated samples. And I used the data from a VADE on syncrude sand to question it. But taking this further now and looking inside some loose samples, this again is on the left, some micro-computed tomography where the void ratio was examined in detail, and on the right a DAM model. And again, you can see that the void ratio is not constant. It varies fairly considerably, and particularly increases on the high side. So that was the syncrude sand data. Very nice publication comparing air pluviated and moist tamp samples was published by Ben Ahmed et al. In 2004. And again, they showed this major difference. So two samples prepared with the same sand, but using different methods of forming the samples, showed quite different behavior. And no suggestion that those two tests would both reach the same critical state. Why? They produced, Ben Ahmed et al., some lovely photographs showing in the A and B, the moist tamped samples, and you can see they're in clusters. There are large voids present. On the right-hand side is the air pluviated sample, the same relative density, showing a much more uniform distribution of voids. They produced this conceptual representation of the aggregate fabric in the lower two diagrams. So the aggregated fabric of the moist tamp sample on the left and the homogeneous fabric, the same void ratio on the right. Now if you take that conceptual picture that they produced, you can identify two zones, a local zone E1 having, a zone having a local void ratio of E1, and the other zone having a local void ratio E2. The E1 void ratio will sit, the state of that material will be within the instability zone. It's obviously waiting to be disturbed. The zone with the high void ratio, the low void ratio, would be outside the instability zone. If you cause collapse for some reason of that open fabric, pore pressure will be generated, pore water will be pushed out of that sample into the neighboring material, and you will increase its effective stress, and it will then reach the instability line. So that's looking at localization at a particle level. Pore pressures migrate under drained, partially drained, or expansive drained conditions to neighboring clusters. The increase in pore pressure in the E2 zone under constant or increasing shear stress and local undermining moves the state into its instability zone and so collapse. So instability lines play a part in explaining the initial local collapse trigger and the chain reaction that follows. Now, presumably a similar process occurs in the field where there is spatial variability and void ratio, and there are void ratio distribution changing. At the field scale, localization will result in progressive failure because of the scale effect. Under maintained loading, the field, global, and even local undrained conditions are more likely to be undrained. Another reason for looking at load control. So going back to our curved critical state line, if you put the global void ratio in, which would apply to the air pluviated sample, you'd be down at the lower of the two blue arrows. If you put the local void ratio in, you'll move up, and you're likely to move into the zone where collapse can occur. So it's the local void ratio, E1, that initiates a chain reaction and is still consistent with critical state predictions, providing you're using the correct void ratio. Somebody else who's done some work on moist temp versus air pluviated samples, showing data from their paper here. The advantage was they looked at different relative densities, 30%, 50%, and 70%. But what they showed is this difference in void space on the left-hand side, the much bigger void spaces in the moist temp samples, and that's backed up by the plots on the right showing the variations in the different regions of void ratio. And those differences start to disappear as you increase the relative density. So it's a problem that applies to low relative densities, to loose samples. They did something else. They looked at the particle orientation in their samples, and they showed for the air pluviated samples, the upper three diagrams, that the particles were very nicely oriented with their long axis horizontal. In the moist temp samples, there wasn't this orientation. It was still a fairly random orientation. Now we know that oriented particles are inherently anisotropic specimens, and they form strong contacts in their long axis direction. And so they produce a support frame in the early stages of shearing, which restrains the contraction of the specimens. So on the right is the air pluviated sample, which doesn't show signs of wanting to contract. In fact, will dilate. On the left is the moist temp sample. Is that not enough to stop people doing moist temp samples? Probably not. If I go to the bottom statement, the critical state approach based heavily on the use of moist tamping reconstitution method is finding increasing application in tailings engineering practice. That was a statement made by David Reed and Fanny quite recently. I question whether that's a good idea. The diagram I've got here was taken from the Bishop lecture by Professor Kaseki, who also used global tomography to look inside these moist temp samples. And he showed that shear bands develop in the loose specimens between the tamp layers. So, you know, if you want to test an unsatisfactory samples, then carry on moist tamping. So, my concluding remarks. Samples prepared by moist tamping or wet tamping are often tested when investigating the behavior of sands and sands with fines, including tailings. The resulting fabric of moist tamped samples does not match the fabric of sedimented samples having the same grading. Clustering results in a non-uniform void distribution in the presence of macro voids. The collapse potential in tracts of compression is exaggerated. Classic investigations using moist tamped samples, such as those by Verdugo and by Jujian, require the conclusions for behavior at the high void ratios to be reconsidered. Sedimented clean sands do not generally show a potential to collapse when tested in tracts of compression, but show a marked anisotropy of collapse potential when sheared after or during rotation of the principal stress directions away from the vertical. This anisotropy results from the preferred vertical orientation of contact normal during deposition and the development of vertical load-carrying columns during overburden loading. This situation can be modified by the addition of fines, depending on the shape and location of the fines relative to the load-carrying framework. And we'll go back to the behavior of micaceous sands, which can introduce a collapse potential even in tracts of compression. So on the left-hand side are two figures, again taken from the Rankin lecture, but this time getting rid of the blue, so you can actually, the blue background, so you can actually see the data. So the upper diagram shows a sand being tested with no mica added to it. Adding 1% of the mica changes its behavior completely. We don't get the dilation. The lower diagram on the left shows the difference between compression and extension when you add mica to the sample. So these are denser samples which will dilate in compression, but collapse immediately on reversing the principal stress direction. And on the right, just emphasizing the importance of fines, and it depends on the size and the shape of the fines, where they are in the structure, whether they're acting as stabilizers or as separators. So just to finish off, the parameters that are used to define the state of soil, such as void ratio, degree of saturation, density, water content, are at best average values. In natural soils and in reconstituted soils below a certain scale, the parameters vary locally. Local variation in void ratio is particularly important in loose material. Macro voids can exist in natural and laboratory-prepared samples depending on depositional environment, including specimen preparation, and post-depositional processes, so stress and strain history. They're large enough to accommodate, these macro voids are large enough to accommodate collapsing particles. Fines can lead to macro voids depending on the shape of the fines and their location in the granular framework. Macro voids close first during consolidation and collapse first during shear. Spatial variability in void ratio distribution determined by grain scale characteristics and formation history needs to be taken into account when explaining observed behavior and predicting future behavior. So void ratio does not convey the fabric of the soil. It doesn't therefore tell us anything about the particle arrangement in terms of the distribution of the different particle sizes. It doesn't tell us about the shape of the particles, the orientation of particles and aggregates and their contacts, or the number of contacts per particle, the distribution and shape of void spaces and the presence of discontinuities. We need to think of something other than global void ratio to characterize our materials, obviously fabric. And fabric is determined by composition, depositional mode, and post-depositional processes, so stress and strain history. Sorry, I thought I'd finished. Critical steady state is reached at large strains, and together with stress level and local distribution of void ratio determines the form of flow in loose sand. Ultimate strengths are poorly defined under load control. Instability, however, occurs at small strains prior to major particle rearrangement, and so before phi dash is mobilized. Reaching the instability surface determines whether flow will or will not occur. The instability line is least affected by localization. The zone of potential instability increases with increasing alpha and increasing global void ratio. Behavior should be linked with the relevant local void ratio. Instability lines have a key role to play in practice, but must consider anisotropy. This is definitely the last slide. And these are not inviting questions. This is, because I don't want any questions. This is just to ask you to think about it. What localization takes place in situ in sands and silty sands? We know what happens in the lab test, but we don't often know what actually is happening in the field. And remembering that suggestion that we should now start using tests which lead to localization, do the kinematics in the field actually match those in the laboratory tests? And the other question, does the chain reaction that seems to explain the response of loose, moist tamp samples contribute to the rapid propagation of tailings dams failures and other flow slides? Thank you for your attention.
Thank you. Just a moment.
So, okay.
You want to see?
No. Absolutely.
Antes de fazermos o agradecimento formal, eu gostaria de dizer umas palavras em nome da BMS. Primeiro, dar uma pequena explicação, né, do histórico. Essa Victor de Mello Lecture é uma homenagem, uma honra a um grande homem, a um grande profissional de liderança mundial e com forte presença no Brasil e em Portugal. Nesse sentido, as duas sociedades, partindo a proposta da BMS, decidiram em conjunto, a BMS e a SPG, a criar a Victor de Mello Lecture. Ela é sempre apresentada no evento Luso Brasileiro, a cada 2 anos e a cada vez num país, no Brasil e em Portugal. Como vocês viram, nós estamos na 9ª Victor de Mello Lecture. Até hoje, todos os palestrantes foram gigantes. Gigantes no padrão do Victor de Mello. O David Haidt mostrou aqui 2 nomes, Jamie Mitchell e o Jamielkowski. Mas todos foram gigantes da engenharia geotécnica. Todos foram exemplos e referências mundiais. Nesse sentido, eu quero pessoalmente agradecer aqui ao Luiz Guilherme de Mello, que desde o início é o grande colaborador, responsável, junto com a BMS e a SPG, da seleção dos nomes, dos convites e de manter a alta qualidade em todas as lectures. Nós podemos ver hoje o nível que tem sido as Victor de Mello Lectures. E é importante também colocar que todas são publicadas na Soils and Rocks, que é um jornal das duas sociedades brasileiras e portuguesa. Então, nós teremos o prazer de ler com toda a calma esta nona Victor de Mello, do David Hyde. Então, nesse sentido, gostaríamos agora de agradecer ao David Hyde. Não sei se o Luiz Guilherme quer dizer algumas palavras antes de fazermos formalmente o agradecimento ao David Hyde.
Acho que eu falarei em inglês, se vocês me perdoarem, meus irmãos portugueses aqui na casa de vocês. It's a pleasure. Roberto said an overemphasized part of my contribution. The first Mello lecture happened in Coimbra. Many of you were present there. Victor was still alive. At that time, there was not the possibility of having, like we are having today, many colleagues are watching live in the LENEC YouTube channel at this moment. At that time, the Portuguese Society, SPG, filmed, and Victor, already in bed, cried for the beauty of the whole surroundings of the first Mello lecture. My contribution has only been and always been in tune with ABMS and SPG in the search of this excellency of which Victor praised so much. So I have to thank ABMS and SPG for the support that it has always given me, not to propose anything, but to try to mend together this search for the giants as mentioned by Roberto. Thank you very much.
Bom, então agora vamos fazer o agradecimento formal ao David Hyde e já convidar a todos para a 10ª Victor de Mello Lecture, que será não no próximo Cobranseg, que vai ser em setembro agora no Balneário Camboriú, mas no Cobranseg de 20 e 26 em Brasília, capital federal do Brasil. Teremos então a 10ª Victor de Mello Lecture. Convido a todos a estarem lá presentes. Bom, David, thank you very much. It was an splendid lecture. We have to take time to read and to go inside of us all the information, all the contribution that you put in this lecture. Really, it's a very, very special lecture. Thank you very much. And you have now just a formal thanks to you. Remember this moment is a Victor de Mello medals and a formal certificate from the Brazilian Society and the Portuguese Society of Geotech Engineering. Thank you very much. Os três aqui, juntos. You take care.
Alexandre,
Please.
let's move there.
Yes.
I'm going to speak without the microphone. David, I was very much. I can go out. I was very touched because you not only raised speculations, but I think you also raised me fears as a professional engineer, being on the necessity of how to estimate the behavior in the field. Fear has to be added to your title. I handle you a copy of another very touchy token. This is the unfinished book that Victor was working when the disease came and he never finished. ABMS sponsored, and we printed his handwritings, whatever was typed, we reproduced it as it was, because I consulted the three first lecturers, John Berland, Harry Paulus, and Mike Jamunkowski. And your friend, John Berland, came with a beautiful phrase. He told me, because I was asking them, would you finish the book, because you know Victor so much? And John came with the saying, the best symphonies, among the best symphonies are the unfinished symphonies, published unfinished. So it's a copy of an unfinished book. And for those who are interested, just enter Victor de Mello website, which is his name, Victor F.B. de Mello. You can download it, you can all have access to it.
Brilliant, thank you very much.
It's an ABMS token.
Right, I shall look forward to unwrapping it.
You will at least see some of the figures.
Because of the people that are
I'm
outside.
sorry.
It's okay.
I don't need to repeat, right?
If you can't hear Lewis, you won't hear me with the microphone. But anyway, thank you very much. Thank you for attending, and yeah, I'm really looking forward to looking at this, together with the book you gave me that you prepared with your sister.
For those who are interested, Victor's biography is also available for downloading in the internet. Just go to the website or go to the International Society webpage. The International Society webpage also has a link for it to be downloaded. Thank you, David.
It is also é importante também dizer que todos os associados da ABMS, a partir do grande trabalho feito pela família Victor de Mello, receberam o livro de memória com toda a história, um belíssimo livro do Victor de Mello. Mais uma vez, thank you, David Hart. Obrigado pela presença de todos. Esse é sempre um momento muito especial para a BMS e para a SPG. Muito obrigado a todos. Obrigado à SPG por esse trabalho em conjunto. Ao LENEC aqui, né, por todo esse apoio.
Muito obrigado, Roberto. Eu vou chamar a engenheira Laura Caldeira e o professor António Gens para fazermos o encerramento do evento. Muito bem, vamos então encerrar o nosso evento, o Congresso Luso-Brasileiro e as Jornadas Luso-Espanholas de Geotecnia. Portanto, em nome da Sociedade Portuguesa de Geotecnia, volto a agradecer a presença de todos, volto a agradecer à ABMS, na pessoa do professor Roberto Coutinho, agradecer à CMSIG, na pessoa do professor António Gens, e um agradecimento muito especial ao Laboratório Nacional de Engenharia Civil, na pessoa da engenheira Laura Caldeira, pela dedicação e pela forma como, brilhante, diria mesmo, como este evento foi organizado, atendendo mais uma vez aos condicionamentos associados. Estamos certos que noutra circunstância, noutra altura do ano, provavelmente teríamos uma assistência ainda mais numerosa, mas o objetivo que a SPG lançou, que foi ter este evento colado ao Congresso Europeu, tivemos uma resposta, enfim, muito positiva das associações brasileira e espanhola e do Laboratório Nacional de Engenharia Civil, portanto, cabe voltar a agradecer. Faço aqui ainda um pequeno parênteses, antes de vos convidar a todos novamente a estarem presentes no Congresso Europeu, que começa na próxima segunda-feira, à questão das revistas. Portanto, foi falado a revista Soils and Rocks. Professor David, you know that you have to publish your paper about this lecture on Soils and Rocks Journal. Thank you very much. Eu apelo também a todos os que estão aqui a publicarem na revista Geotecnia. Na revista Geotecnia aceita trabalhos nas línguas portuguesa e espanhola, e é uma revista também que continua a fazer o seu percurso ascendente, e o sucesso da revista depende muito também dos artigos, da quantidade e sobretudo da qualidade dos artigos que vierem a ser publicados. Finalmente, volto a apelar, antes de passar a palavra aos meus colegas, a uma participação forte de todos no Congresso Europeu, que começa já na próxima segunda-feira. Muito obrigado e até breve.
Bom, eu gostaria, mais uma vez, de agradecer à Sociedade Portuguesa de Geotecnia, à Sociedade Espanhola de Geotecnia, ao LENEC. Foi um trabalho conjunto com a BMS, com muito cuidado, mesmo sabendo de todas as dificuldades que é um evento dessa forma. Mas ele mostrou a sua importância, tecnicamente de alto nível. Então temos que agradecer a todos que participaram, todas as apresentações, os artigos e a organização e esse ambiente extremamente agradável aqui do LENEC. Então, mais uma vez, meu agradecimento a todos, e saio daqui com muita alegria e com muita satisfação e orgulho do trabalho realizado. Muito obrigado.
Bueno, yo voy a ser breve porque las despedidas deben ser breves, pero creo que hemos tenido un excelente día. Hemos tenido unas keynote lectures excelentes, muy informativas, con mucho material presentado de gran calidad, pero también después en las sesiones paralelas, he asistido naturalmente solo a una de ellas en cada una de las sesiones, pero se han presentado casos muy interesantes, ideas muy relevantes, lo que demuestra la vitalidad y la solidez de la geotecnia brasileira, portuguesa y española. And of course, the cherry on the cake has been this. Well, they are always excellent, outstanding lectures, but it was very thought-provoking. You know, since the lecture finished, things are going in my brain that maybe I should revise some of my concepts, some of my ideas, and I think that's the best tribute that can be said of this 9th de Mello lecture. Por lo tanto, eso es todo. Muchas gracias a todos y muchas gracias al enorme esfuerzo del LENEC que ha hecho posible estas jornadas.
Tá Cabe-me a mim encerrar esta sessão. Antes de o fazer, uma vez que já tudo foi dito, gostava apenas de agradecer muito à Comissão Organizadora Especial, ao Engenheiro Bilé Serra, ao Luís Miranda e ao Carlos Pereira por todo o esforço que toda a gente trabalhou, mas essencialmente estas 3 pessoas foram inexcedíveis e, portanto, gostaria muito de lhes agradecer. Também gostaria, por ser neste momento, nestas funções, o último evento em que estamos em conjunto, ao Presidente da Sociedade Portuguesa de Geotecnia, professor Alexandre Pinto, agradecer-lhe muito em nome do LNEC e meu nome pessoal, e bem como à sua equipa, por todo o bem que têm feito pela Sociedade Portuguesa de Geotecnia e a forma como conduziram durante estes 4 anos todas as suas tarefas. Muito, muito, muito obrigado. Acho que é o último instante que estamos juntos nestas funções e, portanto, gostava muito de lhe agradecer. Naturalmente não é sozinho, é a sua equipa e, portanto, os meus agradecimentos estendem-se a todos que com ele trabalharam em tudo isto e, nomeadamente, agora no europeu, que foi um grande desafio e tenho a certeza que vai ser um grande sucesso para todos. Também desejar umas grandes felicidades à nova equipa, que vai assumir as funções da SPG e que podem contar com o LNEC para tudo que precisarem. Muito obrigada a todos e um bom Congresso Europeu. Damos como encerrada a sessão.